We mentioned lattice energy in class and we did a disgusting calculation associated with it. It's an important concept, so it is worth spending a little bit more time on it. Lattice energy is associated with an ionic compound. When you take a gaseous cation and a gaseous anion and you bring them together to make the ionic solid, there's an energy change. That energy change is the lattice energy, and the symbol for it, delta lat H, always measured in kilojoules per mole, and it's always exothermic. You can understand why if you remember that breaking bonds is endothermic. You have to put energy in to pull them apart, so that means when things come together they're going to be exothermic. And indeed, you take a positive and a negative, think about trying to pull them apart, it would be difficult, so bringing them together would be easy, gives out energy. In addition, think about turning a solid into a gas. You have to put energy in. Turning a solid to a gas, sublimation, is endothermic. So when you get the gases going to the solids, it will be exothermic. So lattice energy, exothermic from both considerations. And it's a reflection of the strength of the ionic bond. Last term we talked about bond energies for covalent bonds. Well, the lattice energy can be thought of as being the equivalent. It's the kilojoules per mole required to, if you put it in, required to smash apart the ionic solid. It's also the energy that you get back out per mole when you bring the cations and the anions together. Now, before we move into more nasty, disgusting calculations, we do need to mention a couple of qualitative trends in the size of lattice energy. First of all, charge. As the charge increases on the ions, the lattice energy increases, it becomes more negative, and that should be fairly obvious to you, right? If you've got a 1 plus and a 1 minus and a 2 plus and a 2 minus, you can imagine that the 2 plus and the 2 minus are going to attract each other more strongly than the 1 plus and the 1 minus. And if we look at a little table of these things, so we've got a bunch of chlorides here, Na plus, Mg. 2 plus, Al3 plus. As the charge on the cation increases, delta H becomes more negative. And then I've also got some oxides here, so again Na plus, Mg2 plus, Al3 plus. You can see that as we go 1 plus, 2 plus, 3 plus, the lattice energy increases quite significantly. And we can also compare here the anions too. If we look at sodium with Cl minus, sodium with O2 minus, increase in the lattice energy as we go from 1 minus to 2 minus, and we see that for the magnesium going from 1 minus to 2 minus, and the aluminium going from 1 minus to 2 minus. So as the charge increases, quite understandably, the lattice energy also becomes stronger, becomes more negative. I hope that last trend was intuitive for you. The stronger the charge, the more the ions hold each other together. This next trend might not be immediately quite as intuitive, and that is associated with size. As the size of the ion increases, the lattice energy decreases. It becomes weaker, becomes less negative, and we can see that trend in our little values here. First three values, chlorides, the anion all the way through, lithium, sodium, potassium, are the cations. Lithium is smaller than sodium, sodium is smaller than potassium, and we can see the lattice energy goes down as the size increases. See that same trend when the anion is bromide. Lithium, the biggest one, sodium, the middle one, potassium, the largest ion, has the smallest lattice energy. Swapping the anions now, chloride is smaller than bromide, so lithium chloride has a bigger lattice energy than lithium bromide. As the ions get bigger, the lattice energy becomes smaller. And the reason for that is effectively charge density. If you think of lithium, it's smaller than sodium. Lithium's plus, sodium's plus. The plus on lithium is spread out over a smaller area than the plus on sodium. So the lithium seems to be more positive. If it seems to be more positive, it's got a bigger charge, therefore the lattice energy will be bigger. So a couple of qualitative trends that I want you to know for lattice energy. The first one, intuitive. As the charge on the ion increases, the lattice energy increases. Next one, not so intuitive until you think about charge density. As the size of the ion increases, the lattice energy decreases. So there are the qualitative considerations. However, the quantitative considerations associated with lattice energy are where the real nastiness starts, because you can't measure it directly. So in class, of course, we just treated it as a large HESS'S law application, and that's not a bad way to think about it. So I'm going to go through that again, not using numbers, but thinking of it conceptually. We're going to think of sodium fluoride. So we want sodium fluoride gas plus F minus gas goes to NaF solid, and of course the energy for that is what we're looking for, the lattice energy. Now what we know the sodium fluoride heat of formation, and the equation for that, sodium solid plus a half F2 gas goes to NaF solid. Okay, again, heat of formation is making 1 mole of the substance, in this case NaF solid, from its elements, sodium and fluorine, in their natural states, solid for sodium, F2 for gas, and to balance the equation we have to have half an F2 for the gas. So one equation that we can use that's got some of the interesting stuff, including getting to our product, is the heat of formation. Now notice, of course, that sodium's got to be in the gas phase, but sodium starts off as a solid. So we're going to have to take that solid and turn it into the gas phase, and that's the heat of sublimation. Sometimes you'll see this referred to as the heat of vaporization of sodium solid, more correctly to call it the heat of sublimation, of course. So that takes our sodium into the gas phase, but we don't actually want sodium atoms in the gas phase, we want sodium cations in the gas phase. Well, how do we go from an atom to its cation? That's the ionization energy. So we're going to need the ionization energy of sodium gas to sodium plus the electron. Now, of course, fluorine, ultimately we want to end up with the fluoride, which comes from a gaseous fluorine atom. But of course, in the standard state, fluorine is indeed in the gas, but it's a diatomic molecule. So in order to get the gaseous atoms, we're going to have to break apart the diatomic molecule. One diatomic molecule gives us 2 gaseous atoms, so we'd also need to use the bond energy. Okay. Now, by the way, I should point out that all of these would be given to you in one way or another. It's extremely unlikely that you would have to construct this HESS'S law problem from the start. So anyway, let's call each of those equations 1, 2, 3, 4, 5. Now, strategies to get this, there's lots of strategies to do it. I always like to look at what we're going for, at least as a starting point. And what I see is that we want Na plus gas on the left-hand side. Do I have an equation that's got Na plus gas on the left-hand side? No, but I do have one, equation 3, that has Na plus gas on the right-hand side. So I'm going to take equation 3 and flip it. So now I've got Na plus gas on the left-hand side, I've got an electron that I don't really want, and I've got Na gas that I don't really want. So why don't I get rid of the Na gas that I don't really want? And that occurs in equation 2. If I've got Na gas on the right-hand side, I want to put it on the left-hand side, which means I need to take equation 2 and flip it. Now I've got rid of my Na gases, but I brought in an Na solid that I'd really rather not have. Right, Na solid on the right hand side means Na solid on the left hand side. What do I have that's got Na solid on the left hand side? I've got equation 1, and I don't even have to flip it. Now I've brought in a half F2 on the left that I don't want, and an NaF on the right that I do want right there. So let's get rid of that half F2 on the left that I don't want. In order to get rid of half F2 on the left, I need a half F2 on the right. How do I get a half F2 on the right? Well, I've got equation 5 that has F2 on the left, so I've got to take 5 and flip it. But then I only want a half F2, so I'm going to have to divide it by 2 as well. Okay, and then finally, the last little thing I want, I've got F gas here on the left. I don't want F gas on the left. I've got to put F gas on the right. The only equation left is equation 4. It's got F gas on the left. Flip it, so I get F gas on the right, and now I'm left with that. Okay, now if I look at this whole thing here, just by visualizing it, there's my Na plus gas that I wanted on the left, there's my F minus gas that I wanted on the left, there's the NaF solid that I wanted on the right, a whole bunch of other stuff, but as we add it up, you'll see that that cancels out. The Na gas cancels. After equation 3 was flipped, we had it on the right, now it's on the left. The Na solid cancels because after equation 2 we had it on the right, but then we took equation 1 which had it on the left and cancels those. The half F2's cancel, were introduced in equation 1, removed by flipping equation 5 and halving it, and then finally, not quite finally actually, the F gas disappears and the electrons disappear. So when I add it all up, I get indeed the equation I want. If I'd been giving you numbers, now you could think about the numbers. Let's just do it in a symbolic sense. Equation 3 was the ionization energy of sodium, but I flipped it. So that's now minus the ionization energy of sodium. Equation 2 was the sublimation of sodium, but I flipped it. So now it's minus the sublimation of sodium. Equation 1 was the heat of formation of sodium fluoride. Well, I used that as was. Equation 5 was the bond energy that I then flipped and halved. So therefore the energy of that is minus half of the bond energy. And then finally, I took the electron affinity of fluorine and flipped it. So therefore it's minus the electron affinity of fluorine. And when you add all those flipped energies up, you're going to get the lattice energy. One way that you'll sometimes see this is that the lattice energy is just equal to the heat of formation minus the heat of sublimation minus the ionization energy minus half the bond energy minus the electron affinity. So that's effectively what we're able to do in class. For those of you who took A-level chemistry, you have very nasty memories of lattice energy because it's associated with a so-called BORN-HABER cycle, which is, I think, an extremely elegant way to do what we've just done in the HESS'S law, and that is get the lattice energy of a particular ionic compound by consideration of all those other energies. But instead of putting it in a little line form where we cross things out, it's presented in a cycle. So if we just put that together for what we're interested in, sodium fluoride solid made by sodium plus gaseous ions plus F minus gaseous ions, put them together to get the solid. That is of course the lattice energy. Now that's one way to make NaF solid. Another way to make NaF solid, at least in consideration on paper, is from its elements in a natural state, i.e. the heat of formation. So it's taking solid sodium plus a half F2 gas. Heat of formation goes to 1 mole of the substance that we want, in this case NaF. And now what you do is you just apply HESS'S law, but much more visually, by saying that one way we can go from Na solid to half F2 gas is directly with the heat of formation making NaF. The other way is to construct a big cycle. Now I like to construct the cycle by first of all thinking about the metal and the cation, and then we'll worry about the anion. So we got the metal here that is a solid. Do not want the metal in a solid phase, we want it in a gas phase. So therefore the first thing we'll do is convert that into the gas phase, and that of course is the heat of sublimation. Then I've got the gaseous atoms, but I want the gaseous cations, so that is of course the ionization energy of sodium. If you want a 2+ cation, you've got to have 2 ionization energies, and 3+ cations, you have to have the first 3 ionization energies, and so on. So anyway, now we've got that Na+ that we want. Now let's pay our attention to making the anion from the non-metal, and in this case the non-metal fluorine, which is already in the gas phase, but that's nice. But as we said on the previous slide, it is in a diatomic molecule. So the first thing we have to do is break that diatomic molecule apart to get one of the fluorine atoms. Half of the F2 goes to 1F, and that is of course associated with the bond energy, half of the bond energy, because we've only got to turn half of the molecule into the atoms. Now we've got our cation, that looks good. Now we've got the fluorine atom, which is good. We've got an electron that now we just need to give to the fluorine atom to make the fluorine anion, and that is the electron affinity. So there we are, we've constructed that nice little BORN-HABER cycle, which of course is exactly the same as what we did with HESS'S law, because we've done exactly the same, just presenting it in a slightly different fashion. Now what we do, if we got one of those little equations we're going to put together, is we say, well, one way to go from Na solid plus a half F2 gas to NaF solid is with the heat of formation. The other way is to say, let's do the heat of sublimation, the ionization energy, half the bond energy, the electron affinity, and then of course the lattice energy. We're after the lattice energy, so we'll rearrange the equation so it just becomes exactly the same as what we saw in the previous slide. The lattice energy is the heat of formation minus the heat of sublimation minus the ionization energy minus half the bond energy minus the electron affinity. Lattice energy, important concept. HESS'S law, important concept. HESS'S law applied to lattice energy, rather complicated. HESS'S law via a Born-HABER cycle applied to lattice energy. Cute, pretty, but for A-level students, an exercise in sadism. Hope this made sense. See you in class.